lecture, is it?
Study week.
I think maybe we can finish in 2 lecture for column, or maybe 1.5 lecture. Then we will have slot on for tutorial, yeah, and the examples. Okay, column. So we have done beam, yeah. We have done beam. We have done truss, yeah, and now we go to column. Okay, and this is the procedure in construction. Yeah? You start with the truss, and then go to beam, and then go to column. And the last part of building is what? A footing. Yeah, and you learn how to design footing or how to analyze footing the next semester. Okay. So what's the objective of our lecture for these 2 lectures? Yeah, to understand the theoretical derivation of Berkeley method of column. Yeah, similar to what we have done before. The objective of this analytical lecture is to derive, formula, the relevant formula in a structure analysis. In the last lecture, we derived the formula for force in a member, derived the formula for deflection, and then we derive the formula for deflection of beam. And today we derive the formula for column. Okay. So the formula is this one, yeah, but we will go into detail later to identify the effective length of column or stud, yeah, and to study the type of failure of short and slender column. Yeah, we will have 2 types of column: short column and slender column. In beam, we don't have different types of beam. Yeah, what we have is only the different type of support. In column, we have different type of support, different type of restraint, different type of column length. Yeah, what is column? Yeah, if you refer to textbook or any other literature, you will also come across with the word strut. And in some textbook, yeah, column and strut are discussed in one topic. Yeah, column or strut. So there are various definitions. But for our definition, columns are members that are subjected to axial load, and it is in vertical direction. If otherwise not vertical, it is called strut. Okay, and it is divided into 2 categories: short column and slender column. For short column, yeah, it will fail in crushing, and for slender column, it will fail in buckling. Yeah, and we will see later on, yeah, what is crushing and what is buckling. Yeah, this is introduction to column. Okay, just for information, yeah, on practical aspect of column, yeah, this is concrete column, or what you call it, reinforced concrete column. Yeah, as you know, in concrete structure, yeah, there must be steel reinforcement inside here, yeah, to make it composite. Without steel reinforcement, the concrete will becomes brittle. Yeah, brittle means it is not ductile. Yeah, because concrete is brittle. For structure, we need ductility. Yeah, because if it is brittle, yeah, what happen is, yeah, we will have catastrophic failure or immediate failure or sudden failure. Yeah, you compare between concrete and steel. Steel is ductile. Yeah, ductile. You can bend steel without failure, but concrete, if there is no steel, it will rupture. Yeah, it will rupture. Okay, just steel column. For concrete column, the section is normally rectangular, yeah, or it's solid, rectangular or circular, yeah, or square, yeah, it is solid. But for steel section, yeah, it is called open section. It made of, yeah, flange, web, yeah, thin element, yeah, thin element, and combine into hybrid section becomes I section or H section, yeah, or channel or angle section. Yeah, this is the difference between steel column and concrete column. The advantage of steel column, yeah, it has been discussed in construction material, yeah, and also in first year, yeah, introduction. Okay, what is this? Yeah, this is a truss, a unit of truss, yeah, unit of truss, and this truss, when it is imposed the vertical loading here, this diagonal strut, yeah, it is called strut. This diagonal member will be in compression. This one is in compression. This one is in compression. This one tie, yeah, tie is in tension. Normally, members which are in tension, we call it tie. Members which are in compression, we call it strut. Yeah. So this is called strut. The, the similarity between between column and strut is that both members are under compression. Yeah, under compression. Okay. Okay. This is another information. Yeah. This is still bridge truss. Yeah, still bridge truss. But you see here, yeah, this is the horizontal member. Horizontal member. For horizontal member, okay, the force in this horizontal member is zero. Yeah, when you remember when you learn zero member, yeah, zero member. When at this plane there is no other member, then the force here is zero. But it is still called strut. Yeah, you can find it in internet. There are many information regarding the strut, yeah, column, yeah, tie member. Okay, so why we need to study the analysis and design of column? Because we don't want our um, design. You must do analysis, because without analysis you cannot do design. If you do the wrong analysis, then your design is wrong. When design is wrong, your construction will fail. Yeah, construction will fail. This is the failure. Yeah. So what happened when, yeah, we have this kind of failure? Yeah, the whole collapse. The whole building will collapse. Yeah, the whole building will collapse, and yeah, there might be, yeah, injuries, yeah, or death or fatality. Yeah, and you are responsible, yeah, for that collapse, failure. Yeah. So therefore, yeah, don't be afraid. Yeah. So therefore, you have to do analysis carefully and do the design, yeah, correctly. Yeah, so that your construction will not fail. Yeah, this is your responsibility as an engineer. Okay. Jangan takut pula. Okay. This is concrete column. Yeah, where you see here reinforcement. Yeah. Sorry, reinforcement. You see this reinforcement buckle. Yeah, because concrete is brittle. Yeah, it fail first. Yeah, before reinforcement, but still is ductile. Yeah, due to ductility, yeah, it avoid, yeah, prevent this building from collapse. Yeah, that's the advantage of steel reinforcement. And this is for steel column. Yeah, you see for steel column, it is a small member. Yeah, but it is stronger. Yeah, steel is stronger than concrete. The yield strength of steel is 200 or 400, but the yield strength of concrete is only 30. Yeah, 10 times. Yeah, the strength of steel 10 times compared to concrete. Okay, and this is called member buckling. Yeah, the word buckling, which is the topic of our lecture today, buckling. Yeah, and this is called local buckling. Yeah, we're not going to learn what is local buckling? This semester, this one next year, third year. Local buckling. And this is another failure of member buckling. Member buckling. This is called what? Prop. Prop. Prop is also a kind of strut. Prop is used to support temporarily. During the construction. Prop. Sangga. Okay. So, what is the critical load? We have to learn. We have to derive the formula. Okay. Critical load. Remember, our objective is to derive the critical load. And why it is called critical load? You'll see later. An ideal column is initially perfect, straight, made of homogeneous material, and the load is applied to centroid. And the maximum axial load that a column can support when it is on the verge of buckling is called the critical load. What you are seeing here, this is experimental. This is experimental in the lab. To determine, to study what is the critical loading here. This one. Different types of support. Different type of support of this strut or column. It need different loading. This one is stronger. So you need a much more loading to cause it to buckle. And this is in the lab. And what we are going to do now is not the lab work, but analytical work. This is analytical work. If you combine analytical and lab work or experimental, it is called empirical. Empirical is the combination between theoretical and experimental. What we are going to derive now is merely based on analytical. And it will involve some mathematical derivation, similar to what we have done before for deflection of beam. Very analytical, using some mathematical definition. Okay, so now we are going to derive the critical load. A slender column, slender column, not short column. Slender column pinned at both ends, subjected to axial load here, and it will buckle. The maximum axial load that a column can support when it is on the verge of buckling is called critical load. And additional loading after you reach the critical load, additional loading will cause the column to buckle and deform literally. But in reality, there various formulas have been developed by researcher. It's later. Okay. Now, if we plot between a graph relating the axial load P and the lateral deflection delta, this is lateral deflection delta. Okay. This is the first part of the loading condition. Loading. What is this part? At this part, when you increase loading P, increase from 0, increase again and again, there is no deformation. You can try now, if you have your pen, or your thick ruler, not thin ruler, thick ruler, you apply load. There is no deformation, no lateral deformation. What you have is axial deformation, shortening, no lateral deformation. But until certain limit, where it starts to deform. And this limit is called critical limit. yeah, you start to deform. And once you deform, it will deform more and more monotonically. This is deformation. Oh, sorry, lateral deformation. Okay. But before you reach critical value, there is no deformation. But once you reach this critical value, it will deform tremendously, too much. Okay. This is for perfect condition. Okay. And this critical limit actually is well below the yield limit. For example, this yield limit may be 400. Yeah, maybe yield stress. Yeah, remember when you do you did the tensile test, you have yield stress Py or yield loading. If it is slender, yeah, before it reach yield loading, it start to buckle. That's why we call it slender. It buckle before it reach yield loading. Okay. This one for perfect column. But if you have initial imperfection is maybe some eccentricity, or maybe some initial deformation, or maybe some error in material. This is the real graph. Yeah, where you start with some initial deformation or imperfection, yeah, and then you go here. This is as what has been discovered in experimental. That's the theory, yeah, how buckling occur. Okay. Now, as I mentioned just now, this one is lateral deformation. Yeah, you have another one is axial deformation. Yeah, you have lateral deformation. You have axial deformation. What happened in axial deformation? Yeah, for lateral deformation, yeah, we know that there is no deformation until it reaches pre-critical. But for axial deformation, actually what happened is that, sorry. It is linear. It is linear. Yeah. We call it axial deformation delta. Yeah, linear. Yeah. As, yeah, as long as you increase the loading, yeah, it start to deform, or in this case, shortening or contracting. Yeah, become shorter because it is in compression. This is the difference between lateral deformation and axial deformation. Yeah, and you'll see later in next year, there are another 3 types of buckling. Yeah, this is axial buckling. You will have another type is lateral buckling, axial buckling, and shear buckling, and also local buckling. Yeah, and you have to be patient. That one next year. So for this semester, yeah, we discuss about column or axial buckling or member buckling. Okay, now the theory. So similar to what we have done in the derivation of the deflection of beam, yeah. In theory, we have to principally what is the ideal condition? What's the assumption? Our assumption now is this is column. Our assumption is the column is perfectly straight, no bending or no imperfection, perfectly straight. Number 2, the column is made of homogeneous material. Yeah. Number 1 is straight. Yeah, straight. Number 2 is homogeneous material. What is homogeneous material? Yeah, homogeneous material when yeah, you have equal E value material, Young's modulus, equal E value in all axes, whether in X, yeah, in X or in Y, you have same E value or I. It is what we mean by homogeneous. Yeah, homogeneous. Okay, so if you have material like plywood or material of fiber or mat or maybe bamboo, it is not homogeneous. Okay. Number 3, the load is applied through the centroid of the cross section. Here, the load is applied to the centroid of the cross section. This is cross section. Yeah, this is centroid or center line. Number 4, the material behaves in a linear elastic material. Manner. Yeah, this is linear elastic. Yeah, this is linear elastic. When you do tensile test, this is the first part of the strain stress curve. Okay, when it reach the yield stress, this is the yield point, it will becomes non-linear. And our assumption, our derivation only cover for this linear elastic, not non-linear. Yeah, not non-linear, which means this material is still in elastic condition, not plastic condition. Yeah, here is elastic, here is plastic. And the column buckles and bends in a single plane. What is single plane? This is single plane. Yeah, single plane. Or some, if you refer to some textbook, sometimes it is called single sine curve. Single sine curve. What is sine curve? Yeah, sine curve start with 0. Yeah, start with 0. Different with cos. Yeah, with cos curve, cosine curve. Cosine curve start with 1. Sine curve start with 0 here. Okay, single plane. This is double plane. Yeah, and this is not the assumption. The assumption is not based on double plane. Yeah, but there is a possibility that it will buckle in double plane. Yeah, but when for buckle in double plane, it need more loading, greater loading. Yeah, but we want to find what is the least or the smallest loading. So it must be assumed as single plane. Okay. Now comes the mathematical derivation. It is quite difficult. Okay. A pin and the strut is subjected to axial load. Okay. By using curve equation, this is the same equation. The same equation that we have derived in curvature equation, in beam deflection curvature equation. EI d squared y over dx squared equal to m. And you have P here. You have P here. In beam deflection, is no P. You have lateral deflection. That one beam. For column, the load is axial. So moment equal to minus P multiplied by y. It's a y actually. Y. Yx. Now, uh, you substitute here d squared y plus alpha squared y equal to 0, where alpha squared to p over I. You replace m over p, sorry, m over ei, with this one, alpha squared. And the solution is y equal to a sine alpha x plus b cos alpha x, where alpha is equal to square root p over ei, or alpha squared equal to p over ei. Okay, now similar to what we have done in beam deflection, what is A and B? What is A and B? We know alpha p over ei, but what is A and B? Okay, boundary condition. At x equal to 0 here, y equal to 0. Therefore, b equal to 0. Yeah? You substitute. Substitute x equal to 0. X equal to 0 here. And y equal to 0. You'll find that b is equal to 0. And now the second boundary condition, x equal to L. When x equal to L here, again, y equal to 0. Therefore, a sine alpha x equal to 0. When a sine alpha x equal to 0, is it mean that a equal to 0? No. Yeah. Yeah. If we have a x equal to 0, yeah, then a equal to 0. But a sine alpha x equal to 0, then a might not be equal to 0. Therefore, either a, in which case y equal to 0, or always of x and a star will not buckle, or sine alpha x equal to 0. Yeah. Either a equal to 0 or sine alpha x equal to 0. Okay. So then we got here the least value to satisfy sine alpha x equal to 0 is alpha x equal to pi. Yeah, this is what we mean by sine curve here. Yeah, this is sine curve. Yeah, sine curve. Yeah, what you know about sine curve? Yeah, when angle equal to 0, sine equal to 0, but when angle equal to 90 degree, yeah, uh, 90 degree, the sine is equal to 1. Yeah. Uh, so now come to this equation. Yeah. So the least value to satisfy sine alpha equal to 0 is alpha L equal to pi. What is pi? Yeah. Pi is equal to 180 degree, or yeah, yes, 180 degree. 90 or 90, yeah. Sorry, 180, sorry. So therefore, alpha squared equal to pi squared L squared equal to P over EI, which obtain the least value of the least value. So least value is based on single curve, not double curve, which will cause the stud to buckle, and it is called the Euler buckling load PCR, or some books call it PE, P Euler, or PCR, P critical, or P buckling, pi squared EI over L squared. So this is the formula. So yeah, the formula is not difficult to remember, but the derivation is quite difficult to understand. Eh? Okay. Yeah. And this is what I mean by single curve and double curve. And for this derivation, yeah, we use this first assumption, single curve. So this derivation is for pin here. Okay, what's about fixed? Okay, before that, what is the difference between pin and fixed? In pin connection, the member can deflect, yeah, to form angle here, because it is pin. It can deflect. It cannot move. Yeah, it cannot move, but it can deflect and make angle here. But this is rigid. In rigid connection, the end here, it cannot move, yeah, cannot displace, cannot move, move right and left, cannot move. And in the same time also, it cannot deflect. So it will what? It will keep on straight here. Yeah. It will remain straight here. Yeah. Until at certain point here, until at certain point, it start to deform, deflect. So this is the between pin connection and connection. Okay. Dy squared you have moment here. Yeah, we have moment here. To pick a moment. Okay, we have PCRV. P multiplied by deflection. In here, we have another one is M, fixed and moments. Okay, therefore, yeah, I don't have to go into detail. Yeah, you study this derivation, and at the end, the buckling curve is equal to 4 pi squared EI over L squared, which is, you see, yeah, 4 times compared to pin connection. Yeah, for pin connection, pi squared EI over L squared, pin ended at, and for fixed ended strut, 4 pi squared EI over L squared. Yeah, this is another formula to remember. Okay, and actually, what we can make it easy to remember, why it becomes 4 is because, yeah, the sine curve, yeah, which is formed by the deflection is here. Yeah, this is the sine curve, single sine curve. Yeah, it starts with the point of zero moment here, and if you, yeah, you can use your bending moment diagram. You learn, yeah, you learn bending moment diagram, yeah, in first part of this semester. Yeah, try to draw bending moment diagram. You'll see that there is a point here with zero bending moment, or we call it contraflexure point. And yeah, if you measure approximately this point between two zero bending moment, it is equal to 0.5 L. And therefore, yeah, if you use this pin connection here, you substitute L with 0.5, you will have 4 here. So this is how, yeah, you can easy to remember or memorize. Okay, now we have two condition, pin condition and rigid condition. Okay, we have another. Sorry, before going to another condition. Okay, now this buckling load is given in terms of loading, or the unit is in kilonewton. It can also be given in terms of stress. Yeah, in terms of stress, because in design, you learn design next year. Yeah, uh, normally in standard, yeah, it is based on stress, which is called critical stress. Yeah, you have a critical load. This one is critical stress. So you start from here. Critical buckling load equal to pi squared EI over L squared. But what is the difference, or what is the relationship between, yeah, between I and L? Yeah, uh, uh, stress is equal to P over A. Critical stress equal to P critical divided by A. A is cross section. A is cross section. And what is A and EI and L? Yeah, uh, the relationship between A and EI over L is given here. Yeah, is given here. Yeah, you substitute P critical into this one, you'll get this value, and then but yeah, but yeah, uh, I over A is equal to R squared. and R is called radius of gyration. Sorry, I didn't put the definition of R. R is radius of gyration. Radius of gyration. You got it? R? Or you can refer to a textbook. R is radius of gyration equal to I over A square root. And R squared equal to I over A. And substitute R into here, then you'll get this formula. Sigma CR equal to pi squared E LE over R equal to pi squared E over lambda squared, where lambda is slenderness ratio. What is LE? Yeah? LE is effective length. What is effective length? Yeah? What is effective length? Here we have effective length equal to 2L. Here we have effective length equal to 1. And here okay. If you see this buckling curve, now we change. We change from load and buckling. Okay. If you see this buckling curve, this buckling is derived from this one. Yeah. This one critical, sigma critical. Pi squared E over lambda. Lambda is here. So when you plot this curve, this is the curve. And you see that it will become infinity. Okay. But we have to remember, we have crushing stress. Crushing stress. If you have short column, it will not buckle. You can try. If you have short column, it will not buckle. If you have short pencil, or short bar or member, it will not buckle, but it will fail in crushing or bearing when loading achieve sigma y, reach sigma y, yield stress. Therefore, this curve is only valid for long column and not valid for short column, because this formula is for buckling, not for crushing. Therefore, we divide into two, short column and long column. For long column, we use this formula, and for short column, you just use this formula, sigma y. If the yield stress is equal to 500, then it will only crush when it reaches 500. For long column, maybe it is 200, but it starts to buckle. That's long column. Okay, this is typical, a typical value of curve and also the yield stress here. Look here. Yield stress is about 200. Therefore, for short column, it will crush here. And for long column, it will depend on slender. It will depend on slender. If it is too slender, too long, or too thin, then the critical buckling will be very much lower. Very much lower, but it is infinity here. So this is the typical curve with numerical example. Okay. So what is LE? What is LE? LE is equal to KL, where K, as we have done before, K equal to 1.0 for pin connection here, where L equal to LE, which is that K equal to 1.0. But for rigid connection, yeah, as we have done before also, yeah, LE equal to 0.5 L, where K equal to 0.5. What's about this one? Yeah, this is where pin at one end and rigid at one end. Rigid at one end. Yes, sorry. This one rigid, eh? Oh yeah, okay. Yes. So here LE equal to pin and fix, yeah? Pin and fix. This one pin, this one fix. LE equal to 0.7 L. And what's about when you have cantilever? When you have cantilever, LE equal to 2L. Why it is 2L? Because it is based on, yeah, it's assumed that it will buckle, and this buckling is equal to half sine curve. Half sine curve. Then if you reflect this one here, it will become one single sine curve, which made LE equal to double the length. So this is now you have K equal to 1, K equal to 0.5, K equal to 0.7, and K equal to 2. So this is called effective length LE equal to KL. And this is in design. When you study design next semester, this is different type of end condition. Yeah, different type of end condition. Okay, I think we don't have to go detail. Okay, now what we have done so far is analytical. But as I mentioned in the last in the first two slides, we have experimental and we have analytical. The combination between experimental and analytical, we have empirical buckling. Okay, now what happened to what's about in our buckling curve now? Okay, this is Euler. Euler infinity here, and it is not valid here. This is cut off here. Yeah, and beyond this yield stress value, Euler does not valid. Euler is not valid anymore. Euler only valid for this one. Okay, crushing stress. So this is for short column. This one for long column. Okay. Now, there are many researchers, 100, 200 years ago, 100 years ago, 100 years ago, they do they did many experimental in the lab, full scale and small scale, to find a formula that can be used for both type of column. Now in this formula, we use two formula, Euler formula, and this one is yield formula. Now we try to find a single formula that can cover or that can use continuously from this short column to long column. Short column and long column. And so this is one of the formula. I just take one researcher here, Rankin. There are many more, Rankin. So Rankin used this formula, mathematical formula. And we are not going to discuss about this one. And what I want to show here is only this one. This is Rankin formula. Now Rankin had been successful to derive a formula that can use continuously from short column, cover short column and long column in single formula. This single formula. And so it becomes easier. if you use single formula. Okay, and there are some other formula, tangential curve, many more formula, Johnson formula, Parry-Robertson formula, tangential formula. Okay, now this is ranking formula. Okay, but we are not going to uh, study, or we are not going to use this formula in this semester. This one next semester, next year. Now back to Euler formula. Before we go to example, we look at what is axis and what is moment of inertia. We have done moment of inertia in first year. And we also have done what is major axis and what is minor axis. Okay. Okay. This one is square. This one is circular. For square, I, moment of inertia, Ix and Iy is equal. Similar also to circular, Ix equal to Iy. And for circular, you also have Ixy. If you remember Ixy, Ixy is called torsional rigidity or torsional inertia. This one is moment of inertia. The another one is torsional moment of inertia. We call it J. Or in static, last year, we call it Ixy. You can refer that. Okay. For rectangular, you have Ix, you have Iy. But Ix is greater than Iy. You remember why Ix is greater than Iy? Because it is shorter here and longer here. For this smaller Ix, we call it major axis. And this one is called minor axis. We call it minor axis. So major axis is, it looks shorter, but it is stronger. Stronger. And this is normally for concrete. This three section normally is for concrete. And for steel, we have many type of section. And just to show 5 types of steel section, this one called I section. For I section, this is normally becomes major axis, and this one is minor axis. And this one is called H section. H section. For X, actually, this one for beam, this one for column. This one for column, or also for piling. For piling. For H section, normally Ix and Iy is quite similar. Ix is little bit larger than Iy, but this approximately about similar. Another section is called angle section. Ix equal to Iy, but you have another I is called it's called Ixy. Ixy. This one is called L. Ix greater than Iy. So this one become major, this one minor, and this one channel. This one become major, this one become minor. Why we need to know major and minor? Because in general, buckling will occur, or column will buckle about minor axis. About minor axis. Why minor axis? Because this one. Here. I. Because P critical is the least value or smaller value of Ix and Iy. So it will buckle about minor axis, the axis with lesser I moment of inertia. Okay. So now, what is axis of buckling? For column with pin supported at its end, it will buckle about minor axis IY. However, in general, buckling depends on effective slenderness LE. Yeah, not only I but also LE. Okay, not only I but also on LE. So yeah, these two criteria, I and L, which is the length between restraint point for the respective axis. Okay, this is the pin connection. What's happened if in between the top and bottom pin support, you have restraint here. We call it restraint. Yeah, another member or called secondary member. Yeah, that restrain this column from buckle in this direction. From buckle in this direction. Yeah, which means the effective length now is half. Is half of the L about minor axis. But what about in this axis? In this axis, it is still free to buckle because there is no restraint. Therefore, LEX equal to 1.0 L. Okay. And what's about this case? This case, sorry, I don't know what's mean by annotate the share content. Maybe you can explain to me later. Annotate. I don't know what's mean by annotate. Okay. I didn't know who give me notes just now. Okay. In this case, restraint is about major axis. Yeah. Therefore, for major axis, LEX equal to L over 2, and this becomes strong. Yeah. And also, okay. And another case here. Yeah. The column is restrained at mid height from all direction. Therefore, the effective length is equal to 0.55 L in both direction X and Y. And therefore it will become much more stronger in both direction. So we'll have example how to treat to address with this different type of restraining condition. Okay. You see here, this is one typical example of construction, actual construction. This is steel structure. Here, it is strained in this direction, but not strained in this direction. Here, it is strained in both direction. Strained in both direction. And there are many more. There are many more example here. So depends on what direction of strain, you have to calculate what is the buckling strength. What is the buckling strength? Okay. So before we go to the example, we will have 5 minutes break. And while waiting for the next session, if you have any question, yeah, you can ask now. Yeah, I don't know what's mean by annotate the share content. Maybe you can explain to me later, or yeah, you can ask me now. Yeah, I don't understand. Any question or any particular slide that yeah you need me to repeat? Yeah, no, it's no problem. Yeah, for me to repeat. Yeah. 5 minutes. Yeah. Okay. Okay. Continue. Work example. Example one. A 3-meter long concrete column is having the elastic modulus of 30 kilonewton per millimeter squared. And yeah, about this elastic modulus, you have to be alert. The value of elastic modulus E for different kind of material, different type of material. What is E value for concrete? What is E value for steel? What is E value for aluminium? What is E value for timber? What is E value for copper, and so on. Yeah, and for concrete, yeah, the E value is varied. Varied depends on the type of concrete. Yeah, the grade of concrete. It's normally 30 kilonewton per millimeter squared for normal concrete. Yeah, for steel normally 200. Yeah, for steel it is quite uniform, quite consistent. Different type of steel, but the E value is in between 195 and 205. Yeah, so be careful. This one 30. And the cross section shown in figure is to be used in building. Determine the maximum allowable axial load the column can support so that it does not buckle. The safety factor is taken as 2 given that. Okay, what is safety factor? Yeah. What we are going to calculate is P allowable, P critical, P critical. Yeah. Uh, but the allowable is normally limited to maybe half or 75% of the buckling load. Yeah, it is for safety margin. Yeah, it is for safety margin. Yeah, okay. And given that both ends of the column are pin ends, both ends of the column are fixed end. One end is fixed and the other end is free to move. And this is the section. Okay. Okay. So the first step is to calculate what is moment of inertia. This is the basic equation. Yeah, basic equation that you have to memorize. Yeah. In your first year, you have to derive, and now, yeah, you just memorize. Yeah, no need to derive. Yeah, Ix for Ix, yeah, Ix is moment about, yeah, moment for bending about XX. Yeah, uh, if you remember what is the definition of I, yeah, this is the formula of I. What is the definition of I? Yeah, I is to describe the bending. Yeah, to describe the bending behavior or the bending manner strength of a section or member. So bending means bending about x-axis. Yeah, Ix equal to BH power of 3 divided by 12 and Iy equal to H, where B is equal to 150 breadth, H is the height of this section. And this is the answer. Yeah. Okay. So you have now Ix and Iy. When you have both ends of the column are pin ends, yeah, Le equal to 1.0 L. Yeah, 1.0 L. Here, remember, when it is pin, yeah, it can deflect to make an angle here. Yeah, make an angle. Therefore, it becomes single sine curve. One sine curve, therefore 1.0 L. Okay. So PCR about y-axis is equal to 1301. I don't have to explain this one. And about x-axis equal to 3613. Yeah. Why you have different critical buckling? Because here 70, this one 195. This one major axis, this one minor axis. Yeah. Normally Ix is major axis and Iy is normal. Minor axis. Okay. So the buckling, the smallest P critical is 1301, and this is as what we can easily understand. Yeah, that buckling will occur about minor axis, which has smallest I, and in this case y axis, and in all other cases y is minor axis. Yeah, y is normally minor axis, and yeah, therefore the maximum allowable axial load, yeah, the maximum allowable is divided by 2. Yeah, 650 kilonewton only. Yeah, which mean, yeah, theoretically it can be safe, or it can be loaded until reaching 1301 kilonewton. But in practice, when you do the construction or when you do the design, you limit your loading up only 50% of the yielding point, buckling limit, which means what? You have safety margin of equal to 2.0. This is same thing as in all other design. We have safety margin, not only in civil engineering, but also in electrical or in any other engineering. You have safety margin. Okay. Number 2. Both end of the column are fixed end. Fixed end. When you have fixed end here, it will not displace, prevent from displace, right and left, or prevent from displace in position, but it also prevent from what? Bending here, because it is fixed. You imagine that you hold rigidly in your hand. It will not allow to deflect. So the angle of deflection here is 0 until it reach certain point here where it start to deflect, and this is called 0.5 L. Sorry. I have to correct what I have mentioned just now. It will deflect here, somewhere here, but the sine curve start from here. The sine curve start from here, and this point is called zero bending moment or point of contraflexure. Contraflexure is point, it change from positive to negative, or it change the direction of bending. We change here. This is the point of contraflexure. And when it is 0.5, you substitute into this equation, then you got here 7575. And if you compare to what the value just now, just now you have what? IX 3613. Now, now you have, sorry. 1301, 1301. Now you have 3737, which is what? About 5 times. 5 times larger. When you change this support from pin to rigid, the critical buckling becomes 5 times larger. Okay. Now, in this calculation for B, I calculate only for minor axis. I didn't calculate for major axis because we know already from here, from our experience, that the buckling will be about minor axis. So you don't have to calculate about major axis. If you don't believe me, you can do your homework. You check this one 195, and you replace this one with 2000. See what happened. Okay. So maximum allowable axial load is now equal to divided by 2 equal to 3787. That the allowable buckling load. Okay. Now another one. One end is fixed and the other end is free to move. This is called cantilever column. Yeah, this is called cantilever column. Okay, what example of cantilever column? You can look around around you. Yeah, what the so-called cantilever column. Yeah. Mm. Okay. Uh, have you seen goal post? If you goal post, in football, people playing football, you you see at goal post. Goal post is cantilever column, but cantilever about one axis. Is not cantilever about the other axis. Okay. Uh, so you can look around, find goal post, what's happened to the buckling. Okay. When it is free at the other end, yeah, at both direction, then you will have LE equal to 2.0 L for both direction. Yeah, for both direction, for minor axis and also for major axis. And again, yeah, we also use the minor axis. And this one multiplied by 2, you got here 3 to 5. Because, yeah, why it is 2L? Because it made double sine curve. Start from 0, sine equal to 0. This one equal to pi. Yeah, this one equal to 0 again. Okay, so now you can see here, for cantilever, the value is 3 to 5. Yeah, 3 to 5. But for fixed, the value is 7,575, which is what? Yeah, 20 times. 20 times. Comparison between rigid and cantilever is 20 times. Okay. Okay. This is one sine curve. One sine curve. Okay. That's the first example. Yeah. Maybe we can finish this lecture today. If you can finish today, yeah, we will continue next Wednesday. Next Wednesday with more example. Yeah, on column. Yeah. So this is good for you. Okay. This second example. A 6-meter long steel column having the elastic modulus of 200 kilonewton millimeter squared. Yeah, remember, the unit of E value is kilonewton per millimeter squared. Yeah, or kilonewton per meter squared. Yeah. And determine the slenderness ratio of the column. Determine the critical load if both ends spin. Determine the maximum allowable axial load P allowable. Okay. There is no difference between example 1 and example 2 actually. The difference is only on I value. Yeah. Example 1 is on solid section. Example 2 is on, we call it open section. Yeah. A section with thinner section, or we call it hybrid section. Yeah. Hybrid section, combination of different small section, yeah, and welded together into one hybrid section. Okay. So this is how to calculate the moment of inertia, yeah, which is not our scope of lecture, yeah, because we have covered, this topic in last year, first year. So I don't have to go into detail, yeah. You remember this one, This is for solid section or for single section, and this one for combined section or hybrid section. This one, hybrid mean 1, 2, 3 combined together. Yeah. Then yeah, you have to add another this one, ay bar squared. Okay. And how to calculate this one? Yeah. You can go home, yeah, and make yourself become familiar with the derivation, because in the test or examination, yeah, sometimes you have to calculate the moment of inertia using this basic calculation. Okay. So it will take time. Yeah, it will take time. Yeah. So you must make sure that you are familiar with this formulation. Okay. Now Ix equal to 10 and Iy equal to 1.7. This one 10.3, this one 1.7. Yeah, you see here the difference between Ix and Iy is about what? About uh, 6 times. Yeah, 6 times. And in here, Ix is major axis and Iy is minor axis. Yeah, and as we have done in example 1, we know that the buckling will of course happen, occur about the smallest I or YY axis. Okay. For this section, maybe you ask me, why must we calculate Ix? Yeah, where we know that Iy is normally the minor axis. Why? Because here, yeah, Ix and Iy depends on the proportion of this flange and web. Maybe Iy is greater than Ix. It is possible. Yeah. So we have to calculate first. Yeah. Both of the moment of inertia. Okay. Hmm. Uh, and then, yeah, what is P critical? P critical equal to pi squared EI over L squared. Yeah. So in this case, it is what? It is it both span, both end spin, both end spin, so that yeah, effective length is equal to 1.0 L. Yeah, you got here 94 kilonewton, and P allowable is divided by 2, 47 kilonewton. Okay, that's the buckling load. Okay. The question here is, yeah, determine the slenderness ratio of the column. Slenderness ratio is equal to L over R. Yeah, L over R. Why you need to calculate slenderness ratio? Yeah, because in design, yeah, design formula in standard specification, they use slenderness ratio to calculate sigma stress. That's why we have to calculate slenderness ratio, L over R. And yeah, you also have the definition of effective slenderness ratio. Effective slenderness ratio is equal to LE over R. Okay. What else? And maximum allowable, P critical. Okay. Okay, finish now. Yeah. What example two? Yeah. Very short example. Any question? No question, eh? Hmm. Okay. We are now going to the third example. Yeah. Rods AB and BC have a diameter of 10 millimeter and 16 millimeter respectively. By using a factor of safety of 3, determine the largest load P which may be applied to the structure so that the members do not buckle. Use modulus of elasticity E equals to 200 also shows that the structure will fail due to buckling and not due to yielding of the steel if yield stress sigma equal to 250. Okay, now first look at this structure. Yeah, look at this structure. Is it determinate or indeterminate? Is it stable or unstable? Yeah, it is quite strange, yeah, this structure, because only 3 members. Whereas, yeah, we learned truss, yeah, last week. Yeah, truss should be at least have 3 members to make it triangular. But you you look here. This is spin. This is spin. Therefore, you have 2 reaction here, 2 reaction here. Since we have 4 reaction, it will make this structure to be stable. If you displace it, replace this one with roller, where you have only one, then this structure will collapse here because this one is hinge, or pin. This structure, if you change this to roller, you must change this hinge to rigid or welded. Then it becomes stable. So in this case, yeah, I repeat, since it is pin here, you have 4 reaction. Even though it is pin, this structure is stable. Okay. What's about externally redundancy, indeterminacy? Yeah. We say just last week we say that if there are more than three external force, it becomes indeterminate. But in this case, even though it is 4, but you can still calculate the support reaction. Yeah, support reaction. Okay, maybe you can check. You can check with formula 2m equal to 2m m equal to r minus j. Yeah, you can check that one. Yeah. Okay, now back to this question. Moment of inertia of circular pi dui to the power of 4 divided by 64. Okay, this one also we have to memorize because, yeah, it is not easy to derive. So you have to memorize pi this power of 4 divided by 64. Okay, okay. Sorry. This is error, error. Yeah. Take note, should be only I. There is no AB, no BC. Yeah. Should be only I only. Yeah. Okay. Sorry, yeah. This is I. Okay. Is it correct? Oh, sorry. Uh, okay. Oh, yeah. I hope this is correct, eh? I'll check later. If it is not correct, I'll tell you tomorrow. Wednesday. Okay. Uh, okay. So this is I x equal to iy. Now the analysis. Reaction at support. Yeah. Uh, you take at joint C here. MC equal to 0. Yeah. RA multiplied by 1.2 minus P here. Multiply 1.6 times 1.6, 0. Therefore, RA equal to 0.5. Yeah. And so on. RCX equal to 0.5 P and continue RCY equal to P. Okay. Here, yeah, I said just now that we have reaction here. Yes, in general we have reaction here, but in this case, because because this member is at right angle to this reaction. Therefore, there is no component rectangular component here. Therefore, reaction here is 0. Yeah. Therefore, RAY is equal to 0. Okay. Now, this is your homework. Yeah. You check, you study this calculation of reaction. Yeah. To make it familiar with the force system. Okay. You have two member AB and member BC. Now, both member are in compression. Sorry, I didn't put the compression sign convention here. Both members are in compression. So, both members are subject to buckling or liable to buckling, or possible to buckle. Okay. For member BC, PBC equal to 1.12 P. And for member AB, PAB equal to 0.5 P. After you get the reaction, you can calculate. You can calculate the member forces. This one is theorem Pythagoras. It use resolution method. Resolution method. Okay. And we know that for member BC, the critical buckling is equal to pi squared EI over L squared equal to 354 O Newton. Okay. And using factor safety of equal to 3, allowable P based on P Euler is equal to 1180. So this one is not Euler. Based on P Euler means based on 3450, because 3540 is Euler buckling load. In our scope, all critical buckling is based on Euler, not based on Rankine or not based on Gordon or Perry-Robertson, based on P Euler. Okay. So therefore, P equal to 1053 allowable. This 1053 is when we consider only member BC, but we have not considered member AB. Is it still safe under 1053? Okay, now we check member AB. For member AB, the buckling is equal to 1511.3, 0.3. And sorry, 15113. Okay. And so 0.5 P equal to 15113. Therefore, P equal to 3027 and P allowable is equal to 1007. Which means here, the allowable P when we consider buckling of BC is 1053. And the allowable load of P when we consider AB is is actually only 1007. That means we have to choose the smaller one, yeah, which is 1007. Okay, we choose the smaller one, yeah, to make the two members are in safe condition. Okay, yeah, this is the answer. This is the answer. Okay, I'll check. E-I-E-I. Okay. Member AB, member BC. Oh, you have two. You have two I. Sorry. Oh, I. You have two E value. Sorry. I forget it. You have two diameter. Sorry. You have two diameter now. You have two diameter. One is 10 millimeter and one is 60 millimeter. You have two diameter. Yeah, I think I have deleted the one with 10 millimeter. Sorry. Actually, yeah, we should have another I. Okay. We have two member AB and member BC. Yeah, member AB and member BC. For member AB, yeah, this is the allowable. For member BC, yeah, member BC. Okay. For member AB, 16,000. For member BC, 20,000. Yeah, and P allow. I think I should check. I should check this example. Because I took the example from another lecture note. I should check again this example. Yeah, and I'll come back to you on Wednesday. Yeah, to give you if there any correction here. Yeah. Okay. Sorry for that. Now we go to the last example. Example 4. Yeah. And on Wednesday we will have another lecture, and I'll give it some correction if they need correction, and also some other example on column. Yeah, Wednesday. Okay, this is the for example. A rectangular steel hollow section has the dimension 80 by 100 and 5 millimeter thickness. Yeah, hollow section. Calculate the critical buckling load for the restraining condition shown in figure A, B, and C. Yeah, the column is pin supported at both ends. Pin here, pin here. The elastic Young's modulus E is 200 kilonewton. Okay. Now calculate I value. We have Ix and Iy. Yeah. How to calculate the I value is I of based on external diameter, okay, and then minus deduction, deduction with the hollow. Yeah. And the size of the hollow is 70 by 110. 70 is 80 minus 10, and 110 120 minus 10. And for minor axis, yeah, IY equal to 1.975, yeah, to the power of 6. Okay, now, yeah, I, I put note here, minor axis does not always the weaker axis. It depends on the restraining position and direction. Yeah? Not only position, but also direction. Look at this example. Now we go to A. Okay. In this condition, the column is what? Restrained. Yeah, is restrained about the minor axis. Therefore, this column is restrained from buckle, yeah, about minor axis, which means the minor axis will become stronger. The minor axis will become stronger compared to major axis. Yeah, but what level of stronger? Because major axis is normally stronger than minor axis. Yeah, so it depends on this position of this restraining or the support. Okay, now LEY equal to L over 2. 1.0 is K. 1.0 depends on pin condition. If it is pin condition, 1.0. If it is fixed condition, 0.5. Yeah, 0.5. Okay. Um, therefore, PCX equal to 463 and PCY equal to 794. Okay. And the therefore, the critical buckling load PCR is the lesser of PCRX and PCRY, and PCR in this case is equal to 463. It happened to x-axis. Yeah. Therefore, yeah, in this case, actually, buckling about x-axis is more critical compared to y-axis. Or buckling about major axis is more critical compared to minor axis. Okay. What is mean by minor and major? Yeah? Minor and major depends on the value of I, not depend on buckling. Yeah. So Ix is always major, Iy is always minor, but it does not necessarily. Buckling is about major, depend on restraining condition and position. Okay, similarly, look at B. In B, Lex equal to L over 2 because you have here restraint at mid height. Therefore, L over 2 and Ley equal to 1.0 L per meter, and here and you substitute into here 2 and 4, you got here PCY 2 force 2 force 2 force 3.6 becomes the less or lesser buckling load. Okay, and what happens if it is, yeah, both restrained at mid height? 2.0 L over 2 L over 2 2.0 2.0, then yeah, you substitute into 2.0 here, 2.0 here, and yeah, you have 1853 794 947, and yeah, you see here the minor axis is more critical compared to major axis, similar to what is in general, what is generally happen to uh, pin-ended column. Yeah, uh, yeah, because if you don't have this restraint, yeah, uh, PCY is always critical. If you have restraint, but both direction is restrained, Similarly, we also have y-axis or minor axis is also critical compared to major axis. Okay. So this example again, this example is for pin condition. Pin condition. If it is fixed condition, then you have to replace 1.0 to what? 0. 0.7, or 0.5, 0.7, sorry, 0.7. Okay. Okay, this is just for additional note, and not covered in this syllabus, for eccentric loading, And this is what happened in construction, no? Or in design. If you have here I section, this beam come into contact with this column, not not at the center line, but at eccentric to the center of this section. Whereas this one, it can be connected to the web so that it is positioned at the center of the section. So here, this is axial load, but here it is eccentric load. So when there is eccentric load here, what is or how to calculate the critical load? Of course, it will be less than for axial load. Because we have what here? Initial imperfection, and also you have initial moment. So, I'm not going to explain one by one here. This is just for information, and you will come across with this kind of condition next year, in steel design. And this is the formula given by one of the researcher Webb's approximation. And if you use this formula, you'll find that the critical value here is less than the case of axial load. Okay. I think, that's the end of our lecture today. We have finished the column actually. And for the next Wednesday, uh, I'll check this, this example, a short example, but maybe some error, in copy and paste here. I'll check it again. Any correction, I'll let you know on Wednesday. And on Wednesday also, we will discuss about the assignment that Dr. Yunus has given to you through e-learning. And we also use the times on Wednesday to give more example, relating to column. Okay, before I let you ask question, if there a question, I check the attendant, because I'm not familiar with this one. Kabinesh, are you here, Kabinesh? Kabinesh, I don't know how to check this. Okay, Kabinesh, not here, Kabinesh.
Nama dia ada doktor dekat participant.
Yeah.
Nama Kabinesh ada dekat participant.
I could not read this list of participants. I don't know what happened. Okay. Maybe I I stop sharing first. Okay. FIJK Kabinesh. Okay, you are here. Sorry. Andy. An-Nur Muhammad. Okay. Amir Afwan. Okay. Nur, you was absent last week. Haris.
I'm here, Doctor.
Yeah. Faris ada.
Ada.
Faris ada ya, Faris ada. Muhammad Nuruddin. Ya, Muhammad Nuruddin. Ada apa tu? Apa ni? An-Nur ya, An-Nur. Okey. Muhammad Nuruddin. Ada Muhammad Nuruddin. Okey. Muhammad Nuruddin. Kat mana Muhammad Nuruddin ni? Muhammad Nuruddin.
Ada.
Ada eh? Ada, dalam senarai ni tak ada. Kenapa dalam senarai tak ada? Dia tak faham lah attendant ni. Okey. Saya check lagi eh. Muhammad Ad-Din. Muhammad Faisal.
Ada.
Ada eh? Muhammad Faisal.
Ada.
Ada. Muhammad Adib. Ada. Muhammad Afiq. Tak ada eh. Sini tak ada. Nadrah. Ada. Nur Nadia. Ada. Ada, okey. Terima kasih. Alia ada. Ada. Syakira ada. Wong ada. Yong ada. Muhammad Afiq tak ada. Dan juga tadi Muhammad apa tu? An-Nur ya. An-Nur Muhammad ada.
Ada
An-Nur Muhammad.
Ya, Doktor. Saya ada.
An-Nur Muhammad ada ya?
Ada.
Oh, okey. An-Nur. Okey. Ada soalan? Any question? Kalau boleh dijawab di sini. Kalau tak ada, you keep your question Wednesday. Okay. You read the notes, and make it understand. Or examples. If you didn't understand, then you can we can discuss on Wednesday. Okay. So just one question. You ada cuti study leave tak? Can one of you tell me study leave? Any study leave? No.
Minggu depan
Ada, Doktor.
Ada. Start when it start?
31
Minggu depan. 31
Ya.
bulan.
Next week or next another week?
31 ni, Doktor.
31st.
Next week.
31 Januari.
Sampai 6 Februari.
Sampai 6. Oh, seminggu lah. And then you ada Chinese New Year or exam eh?
7 hari bulan tu dah start exam.
Okay, 7 bulan exam and then Chinese New Year and then you continue with exam. Okay? Okay, so 31 Januari is the date for the study week. Okay. Okay. We see later. We see what we can do for the revision. I hope we can have time or we can have slot for revision before you go for the examination. Okay. So terima kasih. Yeah, thanks for attention. Thanks for attendance. Yeah, see you next week. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih, Doktor.
Terima kasih.
Doktor.
Terima kasih, Doktor.
Terima kasih.
Okay, Doktor.
Thank you. See you. Okay, thanks.